Thanks. Yeah, thanks for the introduction and for the invitation. So yeah, so today I'll be talking about the paper that got accepted earlier this year in SODA. It's a lengthy title called Timeliness Through Telephone. And it's so there's a lot of things going on, but I'll hopefully introduce the problem properly so that you guys have a sense of what it's about, and then go from there. And of course, like I said before, feel free to interrupt me at any time. Definitely want this to be very casual and conversational. Okay. What's this? Okay, let's see. So yeah, so everyone can see the screen, right? Or
Yes,
whatever.
yes.
Okay, perfect.
Yes.
All right, so these are the co-authors for the paper. So essentially it's my PhD advisor, Ravi, with a bunch of other students of his. And okay, so let's start with the problem definition. Yeah. So this problem is really at its root about broadcasting. So let's start with broadcasting. What is that? So imagine that you have a graph, and there's some person, one of the roots, has some sort of juicy gossip message that he really wants to spread to the rest of the network. Except there's a problem that he can't just go ahead and just like kind of put it on, tell everyone at the same time. He still want to keep it as a secret, so he really just want to share with one person at a time. So say his best friend. And now that his best friend, both of them have the message in the first time step, what they can do now, they can tell two of their other friends, like one person each. And then hopefully so now 4 people get the message, and hopefully those 4 people can tell 4 other people, and so on and so forth. So this is what we call broadcasting, that someone starts with a message and your goal is to really tell everyone in the network, but you can only do it one person at a time. Like each person who has a message can only do it one at a time. And then your goal is try to minimize the time it takes to tell everyone the message. Does anyone have any questions? Raise hand or say something if you have any questions.
Dachi, I don't have a question. I have a comment. I think I may have mentioned this other interesting problem to you. So Noga alone had solved this problem. So suppose your graph is the hypercube, right? Let's say the d-dimensional hypercube, right?
Yeah.
And now the model is, okay, let's say the source is outside the graph. Okay, so it's an extra node outside the graph, right?
Okay.
And then the model, if I'm not mistaken, is at so at time 0 only the source. So yeah, there is, as in your model, there is one unique message M, and at every step now in this model, every node U that has the message M can send M to all its neighbors. Okay, to all its neighbors, right? And now you want to again minimize the time by which the last node receives the message, right? And there was a conjecture by Vance Faber that the following lazy, okay, so the only question is what the source strategy should be, right? Because everybody else, they do something very naive. Whenever they get the message, they simply send to all their neighbors and that's it, right? They don't need to do anything, right? But the source can send, I'm sorry. The source can send to any one person at one time. Yeah. So there is the hypercube. Excuse me for this digression, but there is the hypercube. There is a source outside the hypercube. The nodes in the hypercube are constrained that once they get it, they'll send it to all their neighbors in one time step, and that's it, right? And then they can go to sleep. The source, on the other hand, can carefully select one node, just one node at every time step in the network, in the hypercube to send to. And so the only question in the problem is what the source strategy should be. And Vance Faber had conjectured that the following lazy strategy is enough for the source. Take an arbitrary node at time 0 and send to that. And at time 1, send it to the antipodal node, right? Antipodal node to that node, and that's it. The source doesn't have to do anything more. And actually, Noga alone, using what is called the Beck-Fiala theorem in discrepancy theory, he gave like a 1 or 2 page proof of this, basically a short proof, right? And there are some other interesting conjectures about this. We can talk about it later, but just wanted to point out maybe your methods potentially could apply to, this on general graphs kind of thing. You may wish to. If you like, I'll find out the reference and give it to you later.
Yeah, that would be great. Yeah,
Okay.
yeah, I remember talking about this problem before. Yeah, it's definitely interesting because yeah, it's definitely related. Yeah, I've actually never thought about it in the context of what we've done here. But yeah, that's a good point.
Okay.
Yeah.
Okay, thanks.
Yeah.
Please go.
Yeah, perfect. Yeah. Yeah, again, yes, feel free to interject with any comments because they definitely want, like, my goal here is to really introduce the problem to everyone, hopefully inspire you to think about related things or unrelated things. And yeah, so like the more people solve like interested in this problem, the better. That's my my hope from this. All right, so yeah, so let me just do like a tiny toy example here in the graph. So the red node here is a root with a message. So at time 1, he's the only person with the message. At time 0, sorry. So at time 1, he decides to tell to his the left neighbor here. So now the left neighbor, we can mark down that, oh, this is, you received a message at time 1. So we mark down the time when he received the message. At time 2, both of them decide to tell 2 other neighbors. So then, or 1 person each. So then we mark down their time of receival, which is at time 2. And then finally, the last person receives at time 3. So notice that every time, because you can only tell one neighbor, you can only inform one neighbor at a time. So really at each time step, what we're asking for is for you to find a matching in the graph. And then whatever, and then I saw one end of the matched edge has the message, the other end will also have the message. So then the problem can be viewed as given a graph, can you produce a sequence of matchings so that this sequence has you minimize the number of matchings you need to find, like in the sequence, and such that by the end, after finding the sequence, every person has a kind of this like monotonic path throughout the sequence from the root, right? The root can get a message using the sequence of matchings to every person in the network. So that's another way to view this problem. Okay, so what do you what's known for this? Well, on the negative side, we can show that this is an NP-hard problem. And then on the positive side, there exists like log n or log. I think the best right now is something like log over log approximation for this problem. So this is standard broadcasting. So now let me get to the exciting world of vector clock. So what's the motivation there? Imagine that the root no longer just have one message. Maybe he's constantly getting new rumors, right? In our current world, we're always bombarded with information, and new things always pop out all the time. So now instead of just telling the network one particular message, like every day he's getting new messages that he wants to share with the network. So that's kind of the idea behind the model. So then the question is, how do we formalize this, and what are we trying to keep track here now? So here's the situation. Because every day there's a new message being generated, what we want to keep track now is how fresh your information is. So you could have received some information from 9 days ago, but then if you don't hear anything for like forever from then your information will become more and more stale. So it will grow older and older. So then the goal here is really you want to minimize this freshness. So then how does the communication work? So we still want to choose matchings in the network, right? Because you can only tell one friend at a time. And now, so imagine that we have this one edge between 2 neighbors where their freshness, one of them is 9, the other one's 3, meaning that one of them heard it 9 days ago, the other one heard it 3 days ago. So now what happens when they talk to each other? Well, when they talk to each other, the person with really old information 9 days ago, he'll be like, hey, you have something that's more fresh than mine. Like your gossip seems to be better. So that I will learn something from you. Except it takes one time unit for the message to get to me. So by the time I hear it, mine will be 4 days old. And then from the other person's perspective, they'll be like, okay, your information is even older than mine, so I don't care about yours. So mine, I'll just keep my information, and then mine just grows one more day more stale. So mine will also be 4-day-old information in the next time step. Does this example make sense? Any questions?
So are these distinct messages, or should we think of it as some message M that keeps getting refined? So if you
either or, I guess. So
okay.
all you care about is just when's the last time you heard a message.
Okay.
Yeah. So you can treat them as the same message, or I guess it's easier to think of it as different messages being generated at different time.
Okay.
And
but
then,
you only care about getting one of them, and you would ideally like something that is as fresh as possible.
exactly.
Mm-hmm.
Yeah. So formally, you can think of like at every time the root is generating some message, if you currently at time t here's a message from that was generated at time t prime, then your freshness is like t minus t prime.
Mm-hmm. Yes.
And then you want to kind of keep track of this number.
Okay.
And then yeah.
Sorry. In particular, therefore, when you send to a neighbor, I mean, you'll discard it. You'll only keep the latest message you got, right? So of course you won't keep the older messages. Okay.
Exactly. So which is why like when 9 hears it from 3, he will keep the 3, but then because it's 1 day later, so it will become a 4.
Okay.
And then again, and if like mathematically, essentially you're taking the kind of the minimum of the two numbers and then add 1 to it because it became 1 day more stale.
Okay. Thank you.
Yeah. No, great questions. Yeah, keep asking them because I definitely don't want people to be confused at this stage. We're only at the definitions here. So good. Any other questions?
I have a question.
Yeah, go for it.
Is the source node staying the same over time?
Yes, it is. We're gonna treat it as a fixed rooted broadcasting. So that person will stay. The root will be fixed.
Okay, thank you.
Yeah, no problem. Yeah, great questions. Yeah, it's definitely not clear from the way I wrote this. So yes, thanks for clarifying. Okay, good. Any other questions? All right. Okay, then let's continue. So then each person, essentially, we keep track of its freshness, which is why you can think of this. We can store this freshness in a vector, and you can everyone has their own kind of ticking clock that we're trying to keep track of. Hence the name vector clock. So let me actually just do an example here with the same toy example as before. So remember, what's our goal now? It's no longer a finite problem, right? Because we want to generate actually an infinite sequence. Like this needs to go on forever because the information is constantly getting updated. And then in this infinite sequence, you're essentially you're trying to find an infinite sequence of matchings. And then what we keep track of at every time step is this vector of freshness. And then our goal is try to keep this vector, say the max value of this vector, as low as possible throughout all time. Right. So now here's a proposed matching, sequence of matching. It's essentially whatever I was doing before with the broadcast, but let's say I'm just going to repeat it at infinite. Right. So what happened? Well, so at the beginning, we also assume that the roots information is always fresh, so we're not going to keep track of the roots information at all. And then we're going to assume that at the very beginning, everyone's clock starts at 0, right? So in the first time step, you see, so at the very beginning, everyone starts at 0. In the next time step, we inform the left neighbor, so sure, he gets a new information, but he essentially gets information at time step 1. So he gets the information, it takes time to get over, so his information still stays at 1 freshness. Everyone else's information didn't get anything new, so theirs just grow old by 1, so theirs also just grow to 1. So nothing really changes in the first broadcasting of the message. Okay, the second time, what's going to happen is that I'm going to inform these two neighbors. So what happens there? Well, this neighbor, because he gets the information directly from the root, so it's the freshest possible, but it takes 1 time step to get over, so his information will be just 1 day old. Right? This guy, he didn't get anything new, so his just grows old to 2, so it goes from 1 to 2. he does broadcast it to this person at the same time step. So which means that his information will grow. Well, okay, so there's two ways to view this, right? His information, well, when they talk to each other, they have the same information, right? They're both like 1 day old, so it doesn't matter. Like they're not going to get anything new from each other. So that means that his all the information also stays at 2. And then the last person who didn't get anything, it just grows old to 2. Does this make sense so far? Like at the beginning, things essentially, if you're not getting anything new from the root, essentially you're not going to get anything, you're not going to get any updates. So it's not that interesting at the beginning, but it's things do change afterwards, right? Because so for example, okay, so let's do 2 more time steps just to make sure everyone's on the same page. So so at this time we inform this person that this edge is chosen, right? But then because both of them have the same information before, so there's nothing changes, they just all grow old together. No one else getting other information, so everyone's just goes +1 from before. But now in the next time step, that's where more more updates happen, because now I get something fresh again directly from the root. So my information now drop back to 1, while everyone else's information grows old one more time. And then we can see that we can continue this pattern and do the update accordingly. Any questions about this system of updating? So like if I give you a bunch of matchings, like does the update make sense? Okay, no questions. Okay, good. or everyone's really confused, one or the other. So but yeah, so now then if it makes sense, then the question is, okay, how do you come up with this infinite sequence, right? This is no longer a finite problem. We have to find some sort of way to control this or to bound this. What's the best way? Well, over here, what I did is I did kind of the naive thing. Like, well, we know something that seemed reasonable before in the broadcasting world, right? Like we had schedule from broadcasting, and that's a finite thing that hopefully people can solve, and people were able to get good approximation for it. So now, given that sequence, why not just repeat it, until infinity, right? That will give us an infinite schedule. Maybe that will work. And lucky for us is that does work pretty well. Essentially, that's how you can, if you essentially repeat whatever, if you have an alpha approximation for the broadcasting problem, and if you just repeat it like this, you can actually prove that it will never go past, you only double the approximation value. So it's only, so whatever's alpha, then you get 2 alpha. So that's a nice simple result.
Sorry, so again,
yes.
Max broadcast is when we only have one piece of information without continuous updates, and max rooted vector clock is when we continuously keep getting new information.
Yes, okay. Exactly. Yeah, good. Yeah, yeah. It's also good to have this mindset. Like broadcasts will be finite, like you pointed out. So just one shot, and it will be a finite sequence. Vector clock keeps on going forever, and we're looking for infinite sequences or sequences of infinite length. Yeah.
Thank you.
Any other questions or clarifications? Okay, perfect. Okay, so now what does this mean? Like, are we done with vector clock since it's just like 2 approximation from it? Well, not exactly. Let's not do max anymore, right? There are also other objectives we can care about. Max seems to be a bit not fair to everyone, right? What if there's just this one person that's really like far away, or like that's just hard to handle, but then because of that person, we're getting this very high value for max. Maybe there's a bit more fair way of looking at this. For example, average, right? We can think of it as like weighting everyone equally. Then that corresponds to, we're trying to minimize the average value of whatever problem we're trying to solve. Okay, so then why not think about this in the from average, right? Instead of trying to minimize the max of the vector, we try to minimize the average value of the vector, and you minimize, and then whatever the average is, you try to, so at each time step, you get a vector, you take the average of that vector, so then you get a bunch of different values at different time steps, and then you try to minimize the max of that value. So So that will be the average version of this problem. Hopefully that's, yeah, so this, so, oh, sorry, the bar is hiding, but yeah, so this is the average rooted vector clock, right? So now it's the exact same setup here. Here's the toy example, except now I no longer care about the max value. I just keep track of what the average value is, and I try to minimize that value. Any questions about the problem statement? Okay, great. Okay, so so what do we know about average? Well, so of course, related to this average vector clock, we can also talk about the average broadcasting average broadcast time, right? So we call this ABT. So again, this will be the finite version of the finite one-shot version of the vector clock thing. The root has just one message. You try to get to everyone as fast as possible, except you don't care about the max time. You record down once the first time they hear the message, and then you try to minimize that average. So surprisingly for this problem, it's actually, there doesn't seem to be anyone who have looked at this as far as we know, but it seems to be a very natural problem. And so yeah, so even this on its own is an interesting question to study. Okay, and then so now we can ask the same question as before, right? If we were able to get an approximation for vector clock through approximation of the broadcasting problem, can we repeat it here? So for example, if I give you an alpha approximation to average broadcast time, is it possible to just repeat it ad infinitum and hopefully get a 2 approximation for average vector clock? And unfortunately, the answer is actually no here. And this is actually to do with the fact of the average. So if you just think about it, what will happen when you try to repeat something over and over? Think about the very first guy that received the message, right? So for example, this node received the message right away at time 1. But then when will be the next time he hears again? He's not going to be able to hear again until, if I just repeat the sequence over and over, he will only get the message again until I finish running through this entire sequence, and then he will hear the message again. Which means that the next time he hears it, it will not be like 1. It will be like much longer. It will be as long as the max, or as long as the last guy. So then, if you just repeat things like ad infinitum, then you're not going to be able to keep that average low. The first guy will have a very, very high value by the end of this. In fact, like essentially everyone's value will grow to be that very large, which means that you're gonna have a actually quite bad average value. Does that make sense on a high level? Okay, so then the question is, can we come up with something better to do this? So essentially we were able to come up with like a combinatorial way of like essentially given a average broadcast, we were able to interleave it in a very specific way to actually get a log approximation. So it's not constant, but it's a log, but at least that's something. So that means that if we can solve the average broadcast time problem, then we can also get a log n approximation on top of that for the vector clock. Okay, again, pause for questions. Okay, good.
So Dachi, this is interesting, but from what you said before, the static max problem can already be solved within log n over log n. So the average rooted, yeah, I see, not max rooted vector clock. I see. Okay, thanks.
Exactly. So yeah, the question still remains: how do you do average rooted broadcast, right? Like it's still not known. Okay. So yeah, but we'll get to there. And that's actually not, yeah. So let's see. So here are some contributions for this paper. All right. So first this is the result that was just shown. That essentially we can go from average broadcast to average vector clock with a loss of log n. The question is, of course, how do you do average broadcast? So luckily we can also do average broadcast with log squared. So this was essentially building on the technology of max broadcast, which means that combining these two, then we get a log cubed for average vector clock. Okay, but is that really the best we can do for average for rooted for vector clock, for average vector clock, right? Like our current strategy right now is going from to solve average vector clock, we have to go solve an average broadcast first. And then, but then if you do it this way, you have this log-in blow up because of the first theorem. And then so now our natural question to reduce the log cubed is that can we maybe reduce this log-in blow up? And unfortunately, we actually show that this login is not possible. So here's a weird counterexample, is that we were able to actually construct a tree where if you look at the average broadcast value and you compare it to the average vector clock value, there's a login gap or like a omega log gap. So one of them, so that means that here's an example of a graph where if you try to go from the average broadcast time, you have to suffer this log-in loss. There's no way to go around it. Does the statement make sense? Any questions? Okay, so yeah, so that's kind of a bummer, right? That means that but it doesn't. It just means that this way of thinking of always reducing to average broadcast might not be the right way to tackle this vector clock problem. There might be something more direct if you want to get something better. But then the problem, the thing here is that notice that this counterexample is even a tree, and it's not even a complicated tree. I think it only has like 3 levels or something like that, and which means that okay, let's try to simplify things. Can we do something better for trees, for the vector clock problem for average? So so that's essentially our most technical theorem of this paper, is that we were able to get a constant approximation for trees for average vector clock. So yeah, so don't look down on trees. Even though it's a very simple structure, it could still be very, very hard. And for the rest of the talk, or for now, I'll essentially go through some of the proof sketches of this, how we tackle this tree problem. Any questions about everything so far? Okay, good. I hope people are still following. All right. Okay, so yeah, so let's talk about this tree approximation. How do we tackle this? How do we get a constant thing? So I'll break this down into 6 steps of how we solve this problem. And here's the proof sketch. Let me also, how am I doing on time? Okay, good. Perfect. So, okay, what's step 1? Well, we start with a infinite schedule, and it's complicated to deal with things that has infinite length. So we like to deal with finite stuff so we can do some better optimization over it. So let's turn it into a finite schedule instead. So here we're gonna call this a periodic schedule, meaning that so our first goal is to see, is it possible to come up with a kind of inspired by the whole max thing, right? Is it possible to come up with a finite schedule where as long as I just keep on repeating this, it doesn't do that bad? And then it turns out that that is true. We can actually show that there exists a finite schedule where as long as you keep on repeating it, it's only twice as worse as before, as the optimal. So that means now we can just focus our attention to finding the best, most optimal finite schedule and just repeat that. So that's step 1. Okay, so now that we know that we can at least repeat something, is that good enough a structure for us? And can we do even better than that? So that's our next step. We're gonna look for not just periodic, we want locally periodic, which means that wouldn't it be even nicer if instead of just things repeated as one schedule, but like we actually know that every edge, if you look at any edge, the edge always gets used at a very periodic way, right? So for example, like the difference is that in locally periodic schedule, we really want to say that maybe this edge will get repeated every 3rd step, right? But for the periodic one, it could be that maybe the overall we repeat a schedule of length like 20, but within these 20 steps, this particular edge gets used at time 1, 2, 3, and then doesn't get used again until time like 12, 13, and 14. Right, that would be a non-locally periodic schedule. But here we want something even regular. We say that, oh, within this 20 time step window, this edge actually gets used every 4th step. Like that would be amazing, right? That would be even more structure that we can use to talk about it. And lucky for us, we showed that, yes, you can actually find a locally periodic schedule that's, again, another factor of 2 worse than before. So now we can focus on talking about local periodic schedule. Okay, like right now, essentially the first few steps, we're just trying to get more and more structure out of a schedule so that we can actually prove things about it. Any questions about locally periodic so far? Okay.
Really quickly, not about the local periodic schedule, but for the solving the rooted vertex case using the broadcast case, could you just say something about, like, again, how that algorithm is done, or like how that reduction works?
Sure. Right. So you want to go from rooted to broadcast. Rooted
broadcast to
vector clock, right?
Yeah.
Yeah, sure. Yeah. No, great questions. Yeah, like I'm not sure how much detail people want, so definitely ask me questions, and I'm definitely more than happy to go through and talk a bit more about each of the individual proofs. Okay, so it's slightly different. So for max, remember it's very easy. Max, we're just going to repeat things, and then and just by repeating it, we can already get. And if you be a bit careful keeping track of the delay, then we can actually talk. Then you can show that it's within twice. So for average, we know that repeating it is really bad because the very first guy will hear very late, right? So then the idea is, okay, it seems like whoever hears first, we want to repeat it more often than other people, right? And whoever hears it later, we care about them less. We can actually afford to repeat them later. So then on the high level, essentially then what we do is that then let's just bucket them into different buckets of powers of 2 of like how early you want to hear things and how late you want to hear things. So now we get these login buckets, right? Then the idea is, well, since the people who want to hear things early want to hear more frequently, then let's repeat them more frequently, and then repeat the other ones at a longer interval. So now, given this idea, given this like high level idea, then the question is it possible to actually accomplish this and fit everything fit everything together into one schedule? And the answer is yes. So if you're just a bit careful about it, then you can essentially squeeze everyone in exactly perfectly. But the high level idea is that you want to repeat people who hears message earlier, much sooner, and more frequently than other people.
Got it. That makes sense. Thank you.
Yeah, perfect. Yeah. Thanks for the question. Yeah. Yeah.
One more question. So
sure.
For counter example where you constructed for like ABT where you get big O of log n, and then for average RVC where you get omega of log squared of n, is this result specifically when we decide to repeat the algorithm for ABT?
Yeah,
and
great
that's
question.
Where it breaks.
Yeah, great question. So no. So for this result, we actually show that no matter what schedule you try to, no matter what infinite schedule you use, it will be definitely worse than this log squared thing, the omega log squared.
Okay, so this is for a tree, and then the theorem is again on a tree, right? Or on trees.
Yes. So yes, exactly. So this example is specifically for tree, but then because it's already really bad on tree, that means that in general graphs, it's also going to be bad, which is why we focus on solving trees first, and then which is why the next theorem, the positive theorem, would be about we can do it for tree, but this definitely does not say anything about general graphs. General graphs maybe still could be as there might be still a lower bound of like this log n thing, of log n blow up.
Yeah, thank you.
Yeah, no, great questions. Yeah. Anyone else? Yeah, definitely keep them coming. Because yeah, I mean, yeah, like I said, any detail that I'm glossing over that you want to learn more, I definitely wanted to share these information. Okay, great. Then let's keep going. So talking a bit more about about trees, focus on trees. So we went through the first two steps, which is about getting things into a local periodic. So now we're gonna let's see if we can even do better. Is local periodic really enough? We already have edges appearing. Remember what that means is that every edge, we know that it appears, there's a period. It appears like every fourth time, or every like fifth time, or every third time. Is that good enough? Well, here's an example, right? Imagine that the top parent is U and then V. So U appears every third step, and V appears every fourth step. Okay, so what does that mean when we look at the actual schedule? So here U hears a message, and then he decides to here, but then V only yeah, let me clarify again, what does it mean to appear periodically, right? So because we're dealing with a tree, so essentially every edge appearing is you can think of it as if the child of that edge is getting the information at like periodically, right? So here when I say that U is appearing every third time, what I really mean is that it's equivalent to say that the edge that was informing him, he's getting informed every third step, right? And then V is getting informed every fourth step. Does that make sense? Because we're dealing with trees, right? There's this correspondence between the edges and its children. So the roots, not the root, the vertices. Yeah, take time and ask questions. Okay, because so here, so I'm saying that like, so imagine that U is getting information every third step, V is getting information every fourth step, but then what's the actual delay of the freshness of the information, right? Like how much, yeah, what's the delay here? So U hears it here, but then V hears it here. So that means that by the time V hears the information, it'll be one step older, like later than when you got it. So it'll be like, so essentially so if U gets the information that maybe like his freshness is maybe 5, then by the time V hears it, it'll be 6, right? It'll be 1 day later. But then the next time when V hears something, like here, you notice that it will be 2 steps later than when his parents heard something, right? Which means that whatever the freshness is, I have to add 2 on top of it. And then it gets even worse later. So now the next time this child hears it, he doesn't get information from here. He gets information from the previous time, right? Because that's when the communication actually, that's when the last time you heard something fresh. So it'll be actually like 3 times worse than before. Does this make sense? Any questions? Okay, so the point is that even if people are hearing things periodically, because of the bad timing of things, it doesn't mean that you actually will get a very steady delay on top of your parents, right? Your delay, if we look at what's the difference between your freshness and your parents' freshness, it's not going to be a constant difference. It's actually going to vary over time, even though people are hearing things very periodically and regularly, right? Which is not a structure that we really want. We definitely want to be able to say more. Okay, so here's an ideal situation that we want. So here you see that the parent has a period of 3, the child has a period of 6, but if you look at the offset is always the same, right? Meaning that like whenever the child hears information, what's the extra delay he adds on top of it? It's going to be a 2. He doesn't. The next time he hears something, what's the extra delay he adds on it? It's going to be 2 again, right? This will be a very nice structure for us to have. That we want this offset on top of your parents' delay. It's always the same over time. Questions? Any questions? Okay. So this is what the property that we want. We call this like a regular schedule. So on top of every vertex having being informed at a periodic rate, having a period of p, we're going to say that every vertex also have this offset, where essentially you look at the difference between. So the offset is defined as whenever I hear information, I check when did my parent hear that information, and we take the difference. And whatever this difference is, we want this to be a constant throughout the entire schedule. Right? And that's what we call a regular schedule. And we show that there actually exists a regular schedule that's, again, only a constant factor worse than before. So now we can actually focus our attention to finding the best regular schedule. Okay, questions? Okay, good. All right. Okay, good. So yeah, so now, what does this give us? Like, why do we spend so much effort trying to find this regular schedule? Like, it better give us some nice structure, right? So, okay, so let's think about it. Imagine that this is the root, right? Oh, well, okay, or whatever. Like imagine that, yeah, this is a root, and if I'm the child and I have an offset of 2, then what is actually my delay every time I hear something? Well, my delay is always going to be 2. Okay, but now let's push this a bit further. Okay, so now imagine that this parent always has a delay of 2 every time he hears information, and then what would this child's delay be? Well, this child, because they have an offset of 2 again, which means that this child's delay will be 2 on top of it. It will be just 4. So it seems to say that, like, as long, like, if I look at if I want to figure out what is my delay at somewhere later down in the tree, my delay will just be my offset will be just my offset to my parent and then plus my parent's delay. But my parent's delay is just its offset to its parents, like the grandparents' delay, right? So that means that if I want to know my delay, I just need to sum up all the offsets along the tree, along the path to the root. This will give me my delay every time I hear information, right? This is what the regular schedule get us. Does that part make sense? Any questions? Okay, so maybe the detail doesn't matter that much, but yeah, the point is that we can actually write this in a very nice way. The only other thing we have to be a bit careful of is that this only tells us the actual delay when I hear the information, but there's a whole period where I don't hear anything, which means that my delay could potentially be more than that. Well, it will definitely be more than that, but it's not going to be that much worse. It's only going to be as worse as my period itself. So in the end, essentially, I can actually bound what's my delay. My delay will, in this regular schedule, will be exactly the sum of all the offsets. That would be the minimum when I hear it. And then it could be as worse as the sum of the offset plus my period, because that's how long I have to wait until I hear information again. All right. So now what's the average delay? Well, so instead of thinking of average, I can think of just trying to minimize the total sum of all the delay, right? So then if I just add up across all the vertices, essentially I get this formula. It's so here it just means that let's look at the second sum. This is just the sum of all the offset along my parents, along the path to the root, and then I'm just summing over all the vertices. And then because of the tail part, I also have this period that I need to count for. So I also need to sum over all the periods. So this is the total sum for the total delay in a regular schedule. Any questions? All right. Yeah, it's again technical detail, but essentially the point is we can actually write it out in. So we've broken down this infinite schedule into essentially into this one formula, even though it looks complicated, but it only depends on 2 values, right? It's the period and the offset, and we can actually separate them very cleanly into these 2 different sums. So now then the question just breaks down to is, can we just find good periods and good offsets? And then if we can do it, then and build a schedule with good periods and good offsets, and then we know we have this formula, we know exactly what its total delay is, or the average value is. So then hopefully that's something that will give us something that's good. Okay, so that's what all the work so far has been about. Okay, so 3 more steps. So which is essentially first, let's find good periods. Is it possible to actually produce what does it mean to be a good period? So then the idea here is that because we have a tree, So we can actually do some sort of dynamic programming to assign periods to everyone. So we're going to forcibly choose some sort of periods to say that, oh, you're this leaf because you have this many children, you must have this period, right? So throughout the step, we had to actually solve individual linear programmings at every step of the dynamic program and keep track of these values. And we can show that if we assign periods this way, its sum will be relatively nice to the optimal value. Okay, so that's the first step. Then the second step is about the offsets. Okay, so now we assign good periods. Can we also assign good offsets? And then the idea, then what makes offsets nice is that we can actually relate it to the average broadcast time again. So here we can use an average broadcast time schedule to obtain what the ideal offsets that we want everyone to have. And what's nice here is that because we're working with trees, average broadcast time is actually solvable, like perfectly solvable. So that's actually a fun exercise if anyone wants to think about it. For both average broadcast time, like the one-shot thing, and the max broadcast time, you can think about how to solve it on the tree. Both are solvable quite easily. Not obvious, but hence exercise. So yeah, you guys can think about that if you want something to work on. Okay, so now essentially doing it this way, we can actually get this ideal period and this ideal offsets. Then the question is, can we actually build a schedule that have these values? So that would be the final step, putting everything together. We have to ignore some sort of offsets, but that's fine. And then it's just about being very careful about doing that assignment and using these kind of pinwheel type scheduling techniques. We were able to actually find a regular schedule that has these periods and these offsets, the ideal ones that we want. And then with that and this formula, we were able to show that the whole thing is within 4D approximation of the optimal. Okay, so that's a high level, somewhat detailed proof sketch of this theorem. Any questions? Okay. So the remaining part, I was going to talk a bit about I guess I'll quickly talk about this other work. So this essentially wraps up the whole SODA paper. So if you want to read more any of this in detail, just look up the paper with the same title about timeliness through telephones, and you will get more details. Later, with another student of Ravi, Daniel Deroux, we looked at other possible extensions of this work. So I'll just briefly talk about that for 5 minutes, and I'll open up for questions. So here's one variation that might be interesting. It's called multi-commodity, right? So far we've been talking about rooted broadcasting or rooted vector clock, right? Where only one person has a message that he wants to send to everyone. But in general, like a generalized version is that, okay, instead of having one root, maybe multiple people have messages and they want to send to different recipients. So we have these SI-TI pairs that want to, and each SI has a unique message that want to send to TI. But then we still follow the same structure, right? Every time you can only send tell one other person. So that means that every time step we're still looking for a matching. But we don't care about, there's no constraint about how many messages you can send. So even though you could have like k different messages, you can all send all of them at the same time to the neighbor that you're talking to. So this is the multi-commodity problem, and then or setup. And with this, we can again talk about the same problems that we've been discussing. So we can do a multi-commodity vector clock for max, and then for average, and then we can do it for the one-shot version, the broadcasting, and max broadcast, and also average broadcast. And all of these are like somewhat open to be solved. So then what the reason that we worked on this is because some of the theorems before, like this relationship between the one-shot version broadcast and the infinite version vector clock, right? These relationships still holds here, even in this general multi-commodity case. So for max, we still get this 2, like a factor of 2 blow up in approximation. For average, we get this log-in approximation blow up. So that's nice. That means that for either of these problems, we can still just focus on the one-shot version, and that will also give us something for the vector clock version. So okay, so here's just some contributions. So we looked at we started with the max broadcast for multi-commodity because that one still is still open. So we did it for trees and we got a 6 approximation. So again, so yes, just starting off easy to see if we can at least go somewhere even with the simplest structure possible. And note here that we actually couldn't repeat this for the average broadcast, even for trees. And there were just like the whatever techniques we were using, we hit like complications. Okay, so that means if you want to solve, if people are curious, here's an open question: can you do it for trees for this multi-commodity version? And then the next thing we kind of investigated is that is again, can we tackle this vector clock directly without going through the one-shot version? And it was kind of inspired by the whole 4D approximation that I talked about before, like getting this periodic schedule. So is it possible to also get something like that for general graphs? So that's kind of our other big result was that yes, you can actually even for general graphs and for general multi-commodity, you can define this notion of local periodicity, which just means that every edge should appear you know, at a certain period, like with a certain period. So every edge will appear at every 4 times or every 3 times, so on and so forth. And if you can come up with a schedule like that, there actually exists a schedule like this, so that for both problems, you're within like a polylog of the optimal. Which then means that maybe then the way we actually got this is by coming up with like a second order cone integer programming and show that the solution for that is related to these 2 problems and within like a polylog factor. So this gives us another route of tackling the problem, is that maybe you can solve that math program instead and able to, or find an approximation for that math program, and that will also give you a polylog approximation for these problems.
So Dachi, you said second order conic
Program,
conic
yes.
program. Can you define what those are? Or maybe just even informally?
Oh, sure. So the idea is that essentially we want to find, oh right, because you're thinking of each edge, essentially we want to assign periods to each edge. So then you kind of think of it as assigning some value to each edge. And then what are the constraints? One constraint is that because of this telephone broadcasting, you can only inform 1% at a time, which translating to periods just means that 1 over your period, the sum of that should be less or equals to 1. Yes. Because like, essentially you have to break up your time into fractional units to tell each person.
Okay.
So that's one constraint. And then the second part has to do with what the periods means. Is that how does it relate to actual delay of the message, like every SITI pair? That seems to correspond to you want to add up all the periods, right? Like each period, like if I have a period of 3 and you have a period of 4, it seems like it will take a period of 7 for me to get to the next step. So then the idea is kind of you want to minimize this path along the periods.
Okay. So conic programming is that your point should lie within a given cone, basically?
In a given cone, yeah. So then I think where that comes from is because of this like inverse relationship. Like the thing and along the path is about the periods, like you directly summing them. But then the other constraint is like 1 over the periods. You want that to be less or equals 1.
I see.
So because of that relationship, I think that's how you get the cone structure.
And so what is second order here?
The second order has to do with I think it's this multiplication of, so essentially you can think of it as like I have periods and I have frequency, and then frequency are like 1 over the period, and then you essentially want period times frequency to be less than 1.
Oh, the sum of the frequencies. I see.
Yeah, you want the sum of the you want to essentially sum of the frequencies to be less than 1, and then you want sum of the periods to be minimal, and then you relate the two to be like P times F to be 1.
Mhm.
And
Okay.
that's how you get the second order.
Ah, I see. Okay.
Yeah.
And this is actually solvable, this relaxation?
So no, so we do not know how to solve that, and we do not know how bad the gap. Like so I mean, you can get a fractional solution. That's fine, but then we don't know how to round that fractional solution.
No, but can the conic program, which is for the fractional solution, can that be solved? Oh, I see. You're saying the integer program is a conic program.
Yes.
What about the relaxation? How do you solve the relaxation?
The relax. I thought the second. I think for this one, I remember looking. Oh, maybe it's not solvable. I like we definitely were not able to solve it, and I don't remember which part we're stuck at.
I see.
Yeah.
I see. Okay.
Like I in my mind somehow I recall it being like there was some sort of we couldn't round it into a nice solution. Because we also have to try, but I could be misremembering something and confusing the different programs.
So it's not minimizing a convex function subject to the point being in a convex body?
I think it is. I think it is related to that. Yeah, I think it is. I think it is.
Which can then be solved in polynomial time by the ellipsoid method, right?
Yeah, I think so. And then I think the issue was in the rounding. We couldn't round into a integer solution.
Okay.
Yeah. Yeah, I think so. I think that was the issue.
Okay.
Yeah, but yeah, great question. Yeah. Any other questions? Okay. Yeah, so essentially that actually wraps up the whole talk. I'll just finish with some other extensions of works, right? There's actually a lot of different variations of problems, right? We talk about broadcast, we can talk about vector clock, but you see that here you can really minimize, like, for example, the objective, you could talk about max, you can talk about average, but you don't have to stop there. You can do any weighted sum of the value you care about. You can do any LP norm, right? And a lot of these like relationships still carries over for them, so that's nice. And then there's also the like we talk about multi-commodity, which is the most generalized version of the problem. But you can also go a step below that. You can do kind of like all pairs instead of multi-commodity. Then there's also different ways of broadcasting. Here we've been always using the telephone model where you're choosing a matching at a time. But then in kind of like related to the problem Arvin mentioned at the beginning, like what if you're allowed to tell your entire neighbor all at the same time, but maybe have some other restrictions. So that could be there are versions like the radio model or the Wi-Fi model. So that could also be interesting. And those have been studied in the broadcasting world for routed broadcasts for a bit, for quite a bit. So then the same questions could be asked about vector clocks, whether these things still translate or not. And then also you've seen that methods, like I kind of mentioned, like this seems to be like you could tackle it from a combinatorial way, you could tackle it from these like math programming way, and then there's also like graph theoretical structural problems that can also arise from these. So really, there seems to be all these different methods that you can tackle this problem as well. So it's really open for you to explore. And I'll end it here.
Thank you, Dachi. Any other questions? So thank you very much again, Dachi. We look forward to seeing you here sometime in the near future.
Yeah, thanks. Yeah, thanks for inviting.
Okay, thanks again. Bye.
Bye.
Dachi, so I had a question actually.
Oh yeah, sure. Go for it.
So I was just wondering, like the idea that you applied it for the trees case, can it also be like extended to, for instance, like bounded tree width graphs? Because the idea seems like very nice where you're applying this dynamic programming and you're solving an LP in each case, right? So I was just wondering if it can be extended to
Maybe the thing that we heavily that was kind of critical for the tree was this structure that you know exactly how you're getting the information, right? Like because there's only one path to the root. And one problem that we kept on encountering in general graphs is that it's actually just hard to know what the right path is in general. So for example, we were able to show results for general graphs where it turns out there actually does exist a path that you can actually fix the path where you want to get a message from, and even by fixing it, such solution is still within like polylog of the optimal. But then the hard part is finding out what the correct path is. We were always stuck at that step. It seems like whatever method that we try to tackle. So I'm not sure. Yeah, with bounded tree width, like maybe there's still something like so maybe like because another way of solving this problem, like especially with max broadcast, is that they were doing like graph structurally, and they were essentially trying to find a tree that was good to use. So maybe even given knowing more structure about the graph, it's actually easier to find that tree. But yeah, great question.
Okay, thank you so much.
Yeah, no, thanks. Yeah.